When solving polynomial equations, we're going to introduce a few theorems that will help you find the solutions to those equations. The first theorem is our number of solutions theorem. So when we work with polynomial equations, we're working with an equation that's p of x is equal to 0, and p of x represents a function that's raised to the nth degree. So if p of x equals 0, we can say that the polynomial with an nth degree gives n solutions. So you just look at the nth degree, and that's the number of solutions that that equation will have. Now some of those solutions may be repeated, and then all of those solutions are complex, yet some of them may be real numbers. So moving on to the term of multiplicity. When we were talking about that some of the solutions may be repeated, if you have a function that has a solution that occurs more than once, then we can assign a multiplicity number to that solution. For instance, x minus 2 times the quantity x minus 3 squared. If you look at this equation here, we can see that this factor x minus 2 occurs only once, but x minus 3 occurs twice because it's squared here. So this function actually looks like x minus 2 times x minus 3 times x minus 3 again, all equal to 0. So since x minus 3 occurs twice, we say that it has this solution of 3 has a multiplicity of 2. Whereas x minus 2, the solution of 2, has a multiplicity of 1 because it only occurs once. Last theorem that we'll talk about right now is Descartes' rule of signs. And this allows you to find how many positive solutions a function may have and how many negative solutions it may have. So we do that by looking at the variations of signs within this polynomial here. So this is an example of x squared minus 3x plus 2 equals 0. If we look at the change in our operation signs here, so we start out positive and then we're changing to negative, so that's considered one variation. And then we go from negative to positive again, so that's our second variation. So when we have this function which is representative of p of x is positive, we can say since this had a change of variation twice, we can say that it's going to have two possible positive solutions. Now the other part of this theorem says that the number of positive solutions is either equal to the change in variation or it's less than that by a positive even number. So if you say that there are two possible positive solutions for this function here, then we could also say it's a possibility that it may be 2 minus 2, which gives us 0 possible positive solutions. Now the other side of it, we need to find our negative solutions, and so we replace x with negative x. So this is the same as this function here, but it's as if we wrote it as p of negative x is equal to this. And so we have negative x squared minus 3 times negative x plus 2 equals 0. And so when you simplify that, we get x squared plus 3x plus 2, and we need to now look at the variations of signs here to determine our negative solutions. So if we look, we go from positive to positive, so that's not a change, and then to positive again, so that doesn't change either. So in this function here, we don't have any variations in signs, and so we won't have any negative solutions to this equation here. And so when we work through some of the examples in this problem, you'll take a look at how many positive solutions there are and how many negative solutions there are, and if there are any imaginary solutions that are possible as well. So let's try a few examples and put these theorems to the test. For the following polynomial equations, we're asked to find the number of solutions, the possible number of positive real solutions, and the possible number of negative real solutions. So for our first polynomial equation, we have 3x to the fourth minus 2x cubed plus x squared minus 2x plus 3 equals 0. So for our first question, we're asked to find the number of solutions. We can use our number of solutions theorem, and we look at the degree of the polynomial, which it's raised to the 4th degree here. So we can say that there are possible 4 solutions for this equation here. For B, the possible number of positive real solutions, we're going to use Descartes' rule of signs and look at the variations of signs in this first polynomial here. We start positive when we go to negative, so that's 1 variation. Then we go negative to positive, that's 2 variations. Positive to negative is 3 variations, and the negative to positive again is we have 4 total variations for P of x, which is our positive real solutions. And so we have 4 total possible positive real solutions, but the theorem also says that it could also be less than that by a positive even number. So we can go 4 minus 2, which gives us 2, and then 2 minus 2, which gives us 0. So for this equation here, it's possible that it has either 4 positive real solutions, or 2 positive real solutions, or 0 positive real solutions according to that theorem. Now, for the positive number of negative real solutions, we need to replace x with negative x. So we're going to write it as 3 times negative x to the 4th minus 2 times negative x to the 3rd plus negative x squared minus 2 times negative x plus 3 equals 0. So we can simplify this, and we can do this fairly easily. If we look, any of the negative x's raised to an even power, it's not going to change that term, the sign on that term. If it's raised to an odd power, though, it will change that sign. So here, this simplifies the 3 times negative x raised to the 4th power. This simplifies back to 3x to the 4th. But 2 times negative x to the 3rd, this is going to maintain the negative sign there, so we change our subtraction sign to an addition sign, and we have plus 2x cubed. Then again, negative x squared is just x, so this stays the same. We have x squared, and then we have negative 2 times negative x, so this sign changes as well, so we have plus 2x plus 3 equals 0 to finish it out. Now we can look and see if there's any variations in signs in order to find our negative real solution. So let's look here. We have positive to positive, that stays the same, to positive to positive to positive, it all stays the same. So there are 0 possible negative real solutions. So 0 negative real solutions. That's our answer to part C for this first equation. So let's move on and do the second equation here. We have x to the 4th plus x squared minus 1 equals 0. And looking at this here in this polynomial, we have 2 terms, x to the 3rd, which has a coefficient of 0, and x, which has a coefficient of 0. And we're not going to bother with those in order when we're looking at our variations and signs. We're just going to go straight from the first term to the second term. But first, let's look at our total possible solutions for part A and our number of solutions theorem. We look at our degree 4. So part A, we have 4 possible solutions here. Now part B, we find our number of positive real solutions by looking at our variations in sign. So we go positive to positive, that doesn't change, but then positive to negative here, that's 1 variation. So our answer for B is 1 possible positive real solution. And then just as we did in the previous problem, let's replace x with negative x in order to find our possible negative real solution. So we have negative x to the 4th plus negative x squared minus 1 equals 0. Simplifying this, since our powers are all even, this simplifies back to our original equation. And then we look at our variations in sign. Again, positive to positive is no change, but positive to negative here is 1 variation. So we have 1 possible negative real solution. And there you go. One other thing to note too, that if you're dealing with a problem that has, let's look at this second one that we just did. It has 4 total possible solutions, but when we looked for the real solutions, we only got 1 possible for positive and 1 possible for negative. So that means that there are some extra solutions out there that we would need to figure out, and that's where the imaginary solutions come into play. So pay attention to that and see if any of those pop up when you're working through the problem set. Let's move on, and we're going to talk about one more important theorem. Now, the rational solution theorem is a way to list all of the possible rational solutions for a polynomial equation. And we do that by saying P of Q is a solution to this polynomial equation. If that's true, then P is a factor of the constant term A sub 0. And then Q in the denominator, that's a factor of the leading coefficient of our first term in the equation, A sub n. And then we can use our values for P and Q, put them together in order to find possible solutions for this equation. So let's go ahead and try an example using this theorem. Okay, for this problem, we're asked to solve x cubed minus 3x squared plus 4x minus 12 equals 0, and we need to solve this completely, so we need to find all of the solutions. So let's start by listing what we know. We can look at the degree of this polynomial equation here. It's raised to the 3rd power here, so the total possible solutions we can write as 3. Then we can use Descartes' rule of signs, and we can look at the total possible positive real solutions by looking at the variations of signs in the equation. So for the positive real solutions, let's look. We've got positive to negative, that's 1. Negative to positive, that's 2, and positive to negative, that's 3. So we have 3 possible positive real solutions, but we also have 1 possible positive real solution because it's either equal to the number of variations in signs here, or it's less than that by a positive even number. So 3 minus 2 gives us 1. Now for our negative real solutions, let's substitute negative x in for x here in this equation. So we have negative x cubed minus 3 times negative x squared plus 4 times negative x minus 12 equals 0. Simplifying this, this is an odd power, so this is going to change the sign to x, negative x to the 3rd. Minus, here we have an even power, so this sign doesn't change. We have negative or subtracting 3x squared. And then here we have an odd power, so this changes to negative 4x. And then the rest of it is minus 12 equals 0. So now if we look at the variations in sign in order to find our negative real solutions, we have negative to negative, to negative to negative. They're all negative across the board, so there are no change in signs, and so we have 0 possible negative real solutions. So let's plug this information into a table here. Okay, so we have our first, we've got a possible 3 positive real solutions. And if we line that up with our possible 0 negative solutions, if we look at the total that we have here, we have 3 solutions total, and that equals our total possible solutions. This line here is for both real and imaginary solutions. So since we have all of our solutions covered with our positive and our negative here, that would mean that if this were the solution route for this equation, we would have 0 imaginary solutions. Now, if we were to go to this 1 positive real solution possibility, we would put 1 here. We still have 0 negative solutions, but that leaves 2 remaining solutions to find. And so we would put that 2 here, which means that this row would allow for 1 possible positive real solution and then 2 possible imaginary solutions. So now let's move on and we'll do the rational solution theorem. We're going to plug in our values for P and Q. I've written them out here to save us time. For P, this we want to say that it is equal to a factor of our constant value, which is negative 12. Our A sub 0 value is up here. And so the factors of negative 12 could be plus or minus 12, 6, 4, 3, 2, or 1. Now for Q could be a factor of the leading coefficient in our equation, A sub n. And the leading coefficient up here is just 1. So factors of 1 is positive or negative 1. Okay, and then we plug these values in for P over Q. So our possible solutions to this equation here could be positive or negative 12, 6, 4, 3, 2, or 1, because I put the values of P over the values of Q, and that's what we get there. So now let's choose a couple of these possible solutions, and then we'll do some synthetic division in order to find and see if we have a remainder of 0, which would mean that they are a solution to this equation. So let's choose the factor of 2. Let's say we were to do some synthetic division with this factor. We were going to divide this polynomial by x minus 2. So let's pull down our coefficients. We have 1, we have negative 3, we have 4, we have negative 12. And then working through our division here, bring down our 1. 2 times 1 is 2. Negative 3 plus 2 is negative 1. 2 times negative 1 is negative 2. 4 plus negative 2 is 2. 2 times 2 is 4. Negative 12 plus positive 4 is negative 8. So it means we have a remainder of negative 8, which then eliminates 2 as a possible solution for this equation. So let's try one more. Let's try 3. If we were to plug in 3 and do the same process, so we have our coefficients again are 1, negative 3, 4, and 12. Again, those are the coefficients of our terms in our equation here. Bring down our 1. 3 times 1 is 3. Negative 3 plus positive 3 is 0. 3 times 0 is 0. 4 plus 0 is 4. 3 times 4 is positive 12. Negative 12 plus positive 12 is 0. And look at that. We have a remainder of 0, which means that 3 is a solution to our equation. And we can use this answer here, 1, 0, and 4, and create our other factor. And so we can rewrite this equation then factored as x minus 3 times x squared, this is the coefficient here, and then we have the 0 coefficient for our x term, so we won't write that at all, it's eliminated, and then we have 4 as our constant. And this is all equal to 0. So then we can set these two factors equal to 0 and solve for x. So we have x minus 3 equals 0, and that gives us our solution that we just found because of our synthetic division, x equals 3. Let's also set this parenthetical equal to 0. We have x squared plus 4 equals 0. And solving for x, we have x squared equals negative 4. If we were to take the square root of each side, then that leaves a square root of negative 4, which means that we have x, and we can simplify this side using some imaginary numbers. So we have, this is plus or minus 2i, which then falls in line with our second row of possible solutions here, because we have one real solution where x equals 3. This is our positive real solution. And then we have 2 imaginary solutions, either positive 2i or negative 2i, and that falls in line with this third column here. So this is how you put everything together using all the theorems that you've learned in this section in order to solve this polynomial equation.